We want to sketch the graph of the function f of x equals 5x over x squared minus 36. Now this is a rational function because it has a variable in the denominator. I'm going to start with finding the domain of this rational function. With rational functions, we're concerned about the denominator equaling 0. So I'm going to start by setting the denominator x squared minus 36 equal to 0, and I'll solve. I can solve this by factoring. It factors to be x and x, 6 and 6 with a plus and a minus. This is a difference of squares. And then we'll use the zero product property and set each factor equal to 0. I'll subtract 6 on each side to get x equals negative 6, and I'll add 6 on each side to get x equals 6. This gives me the restricted values. These values will cause the denominator to equal 0. Division by 0 is undefined, and so these values have to be excluded from the domain. So I'm going to write my number line, mark negative 6 and positive 6 on that number line, and I'm going to shade everywhere else. All of the other values on this number line, besides negative 6 and 6, are included in the domain. So we want to represent each one of these shaded regions as a part of the domain. And we're going to represent them in interval notation. And interval notation has a lower bound and an upper bound. So this first interval, this arrow indicates it's going on forever. So that first interval starts at negative infinity. It stops at negative 6. We use a parenthesis to indicate that negative 6 is not included in the set. The next interval is negative 6 to 6, and the next interval is 6 to infinity. So this is the domain. The domain of this rational function is negative infinity to negative 6, union with negative 6 to 6, union with 6 to infinity. More simply stated, it's all real numbers except for negative 6 and 6. So now that we found those restricted values of negative 6 and positive 6, I want to figure out what type of restricted value they are, in the sense that we have two options. They can be a hole in the graph, or it can be a vertical asymptote. So I want to figure out which one. In order to determine which one, I want to write my function in factored form. So I'm going to start with that 5x in the numerator. 5x is already factored. And we've seen that we can factor x squared minus 36. It's a difference of squares. X minus 6 times x plus 6. And once we have it in factored form, we're going to look for common factors. So if we have common factors, that's an indication that we have a hole in the graph. And since we don't have any common factors, we have no holes. And what that tells me is that these two restricted values that we have are both going to be vertical asymptotes. Since we don't have any holes in the graph, since there are no common factors, these restricted values of negative 6 and positive 6 are vertical asymptotes. Now that's important in sketching the graph, because that tells us how to draw the graph near these values. So we know because there is a vertical asymptote at x equals negative 6, as x gets close to -6, our y value will approach infinity, or y will approach -infinity. And the same thing goes with +6. Because there's a vertical asymptote at x equals 6, we know the behavior of y near that value. As x gets closer to 6, y will approach infinity, or y will approach -infinity. We'll take a look at that a little bit more as we continue to draw the graph. The next thing that we're interested in is if this function has a horizontal asymptote. In order to determine if it has a horizontal asymptote, we're going to look at the degree of the numerator, which we call n, and the degree of the denominator, which we call m. So what we look for in our function, we look for the power on x. So in the numerator we have 5x, and the power on x is a 1. So the degree of the numerator is 1. In the denominator, we have a power of 2 on x, and then a term with no x. So that means that our degree is 2. We take the higher power. Once we've determined that degree of the numerator and the degree of the denominator, we need to compare them. And there's one of 4 cases that we're hoping this falls into. In fact, we're sure it's going to fall into one of these cases because this covers every possible scenario. So these are the 4 cases that we pay attention to. The first one is n being less than m. The degree of the numerator is smaller than the degree of the denominator. The second case we pay attention to is when the degrees are equal to each other. So the degree of the numerator is equal to the degree of the denominator. The third case is that n is m plus 1. The degree of the numerator is 1 more than the degree of the denominator. And then finally, this is the one that fills in the gap of every other possibility, that n is greater than or equal to m plus 2. So this is saying that the numerator would be larger than the denominator, and it's larger by 2 or more. So looking at our situation, we have n being 1 and m being 2. N is less than m. 1 is less than 2. And so we are dealing with this first case. Now, once we know we're dealing with the first case, we have memorized a set of rules for each one of these cases. Now, the reason why we're memorizing these rules is because the actual math behind finding the horizontal asymptote involves an operation called the limit, which is a calculus operation that we haven't introduced. So we've summarized these rules so that we don't have to deal with that operation in this algebra class. So the rule that we have memorized is that anytime n is less than m, the degree of the numerator is less than the degree of the denominator, we will have a horizontal asymptote, and that horizontal asymptote occurs on top of the x-axis, which is the line y equals 0. So this function will have a horizontal asymptote at y equals 0 because the degree of the numerator is less than the degree of the denominator. The next thing that we're interested in is determining if our function, if the graph of our function crosses the horizontal asymptote. So to have our graph cross the asymptote, we're going to create this equation where we set the function equal to the horizontal asymptote. That's going to give us 5x over x squared minus 36. That's our function. We want to see if it crosses the asymptote, and that horizontal asymptote is at 0. So if we solve this equation, we're going to find out if the graph ever crosses that asymptote. So to solve this, I would multiply both sides by x squared minus 36. That will eliminate the denominator. So we cancel out that denominator. We're left with 5x on the left. On the right, 0 times anything is 0. And we have this equation, 5x equals 0. We'll divide both sides by 5, and we get x equals 0. So because we got a solution here, we do know that the graph will cross the horizontal asymptote at x equals 0, and we can find the y value at 0 because that's where the horizontal asymptote is. So this is the point where the graph crosses the horizontal asymptote, y equals 0. The next thing we're interested in is if this function has any intercepts. So we're going to look for x and y intercepts. So we look for a y-intercept by letting x equal 0. We're going to substitute a 0 into our function. That would give 5 times 0 over 0 squared minus 36. That's 0 over negative 36, which is 0. So the ordered pair 0, 0 is a y-intercept. Then we're going to look for x-intercepts. We find x-intercepts by letting y equal 0. We're using function notation. So f of x is our y. So we're setting f of x equal to 0. That would give us the equation 0 equals 5x over x squared minus 36. That happens to be the same equation that we just solved over here. So we already know the solution to that equation is going to be 0, 0. So we have 0, 0 being an x-intercept. It's also the point where the graph crosses the horizontal asymptote, and it's also the y-intercept. So we've seen that 0, 0 show up in those places. So now I think we're getting closer to sketching the graph. So let me put on the screen here a grid for us to use. We can make that a little bigger. So let's start writing down what we've learned so far. So we have learned that we have vertical asymptotes at x equals -6 and +6. So I'm going to draw a vertical dashed line at x equals 6 and a vertical dashed line at x equals -6. These vertical dashed lines are going to act as guides on how to draw the graph. We also have found that this function has a horizontal asymptote at y equals 0, and that is right on top of the x-axis. Let me label these. We have a vertical asymptote at x equals -6, a vertical asymptote at x equals 6, and a horizontal asymptote at y equals 0. We also have found this ordered pair, 0, 0, is a special point. It is the point where the graph crosses the horizontal asymptote, it is also the x-intercept and the y-intercept. So this is all the information I have so far, and I don't feel confident in drawing the lines at this point. What I'm looking for is to have some ordered pairs in every one of these sections that are divided up by the vertical asymptote. I do have one point in this middle section, but that one point is not really enough for me to know how to draw the line. There are just too many choices. I'm not sure if I draw the line going to positive infinity or if I draw the line going to negative infinity. So I need some more information because there's too many choices. And the same thing goes with these outside sections. I don't have any points in this section or this section to help me decide whether to draw the line going to positive infinity or negative infinity, positive infinity or negative infinity. Like I said, too many choices right now, so I need some more information. So what I'm going to do is I'm going to choose some points in each one of these intervals. So I need to pick a value that is less than -6, like -7. In the middle here, I want to pick a number in between -6 and +6. So maybe I'll choose negative. Actually, it might be easier if I choose some, yeah, let's do -5 and +5. And then in this last section, I need to pick a number that's greater than 6, like 7. So I'm going to pick these values for my x's, -7, -5, 5, and 7. We're going to substitute it into our function to get the y value. It's 5 times -7 over -7 squared minus 36. 5 times -7 is -35. -7 squared is 49. 49 minus 36 would be 13. And we're going to get an approximation of that with our calculator. 36 over 13, we get a -2.8. We'll do the same thing with the rest of the values. We have 5 times -5 over -5 squared minus 36. That's -25 over 25 minus 36. 25 minus 36 is -11. And this 25 should be negative. 5 times -5 is -25. So 25 divided by 11, we've got a positive 2.3. We have 5 times 5 over 5 squared minus 36. It's 25 over 25 minus 36. 25 over -11. We have -2.3. Last one, 5 times 7 over 7 squared minus 36. That's 35 over 49 minus 36. 35 over 13 would give me a positive 2.8. So now we have some more ordered pairs, and this will help guide us on drawing the graph. We have -7, -2.8, should be about right here. We have -5 and 2.3, should be about here. We have 5 and -2.3, be about here. And 7 and 2.8 would be about here. Now that I have these points, I feel more comfortable drawing the graph. Now, using my asymptotes as guides, remember the definition of our asymptote says that as x is approaching that asymptote, y will approach infinity or negative infinity. And now I know which one to choose based on where my point is. So that point that I plotted is in the negative, so I know that my graph will be approaching negative infinity. And this point is in the positive, so I know the graph will be approaching positive infinity on that side. And we can do the same thing here. This is in the negative, so the y will approach negative infinity. This one's in the positive, so it'll approach positive infinity. In the middle, I can connect these points. Those 3 points get connected, and then the definition of my horizontal asymptote is that as x approaches infinity or x approaches negative infinity, y will be approaching 0. So I know that my graph will start to approach the horizontal asymptote on both ends. And so now we have a sketch of our rational function 5x over x squared minus 36. Thank you for checking out my videos. Have a great day. For this question, we were given the graph of a quadratic function that you see on the left. And we want to answer the following questions. We want to state what the vertex is as an ordered pair, state the domain in interval notation, state the range in interval notation, and state all intercepts as ordered pairs. So we're going to start with the vertex. Now the vertex of this graph will be this point right here. We can think of it as the bottom of the valley. If it were a down-facing parabola, it would be the top of the hill, top of the peak. So I can read the ordered pair from the graph here. It has an x-coordinate of 1 and a y-coordinate of 4. So the vertex of this quadratic function is the ordered pair 1, 4. The next thing we want to find is the domain of this quadratic function. Now we're going to assume that these are arrows going on forever. And if we use our ruler, we can take a look at holding that ruler vertically. And when we're holding the ruler vertically, what we're paying attention to is that vertically it's marking out different places along the x-axis. And that's important because the x values are what makes up the domain of a function. So when I'm holding this ruler vertically, I'm going to sweep it from left to right and pay attention to when my ruler starts hitting the graph and when it stops hitting the graph. So because of these arrows going on forever, it's going to keep going up and to the left and up and to the left. That means that there is no real starting point for the domain. We say that it begins at negative infinity. And because of this arrow here, it's going to continue to go up and to the right. There's no stopping point for the x values. So it goes from negative infinity to infinity. That's all real numbers. For our range, we'll hold the ruler horizontally. And when we hold it horizontally, this is marking out different places along the y scale, which is important because the range marks out the y values that are on our function. So we notice that down here at the bottom, we don't have any piece of the graph. So the range is not going to start until we get to that vertex. Remember that vertex was at a y value of 4. So that's where our range is going to start. And this point, the vertex, is on the graph, and that means 4 is going to be included in the range. And so we put a bracket on the 4 to indicate that 4 is in the set. So 4 would be the lowest y value, and then because of those arrows continuing to go up and up forever, we have no stopping point for the range, so we mark that as infinity. So our range goes from 4 to infinity, including 4. Then finally, we want to state all intercepts of the quadratic function. So we have X-intercepts and Y-intercepts. X-intercepts are where your graph crosses or touches the x-axis, and Y-intercepts are where the graph crosses or touches the y-axis. So I'm taking a look at my x-axis to see if the graph ever crosses or touches the x-axis. You can see that the graph is well above the x-axis and never crosses or touches it. So we have no x-intercept. We'll do the same thing for the y-axis. So for the y-axis, I'm going to take a look and see if the graph ever crosses or touches the y-axis. You can see here the graph crosses the y-axis at a value of 5, and we'll write that as an ordered pair. That is 0, 5 for the y-intercept. Consider the quadratic function below. Graph the function using transformations. We have the function f of x equals x minus 7 squared minus 9. Now we've already been told that this is a quadratic function, but if we weren't told it's a quadratic function, you would notice this squared, and that would indicate what your base function is. So our base function is y equals x squared, call that the square function, and the graph of the square function has a parabola which has a vertex at 0, 0. Now this is important because we're going to transform this graph by shifting or reflecting or stretching and compressing. And if we know what the graph starts looking like, it's going to help us to understand what to transform to. Now looking at this example, I can see two transformations. We've got this minus 7 and minus 9. Maybe I should put those in different colors. So the minus 7 and minus 9, they are both in the category of shifts for this transformation. And the reason why I know they're shifts is because shifts will happen whenever you add or subtract to your base function. So we have minus 7, that's subtracting, and minus 9, subtracting, and so I know that I have shift. Now there are two types of shifts. You can have a vertical shift, which means that you're shifting up or down, or a horizontal shift, meaning you're shifting left and right. And we can distinguish between those two types of shifts based on where the adding happens. So if we focus on this squared, we can see that this minus 7 happens inside of the squared versus the minus 9 happens outside of the squared. Or in other words, the minus 7 is affected by the squared, where the minus 9 is not affected by the square. So whenever we have the whenever we have adding or subtracting that is inside the base, inside the square, we know that that is a horizontal shift. And whenever we have one that is not affected by the squared or outside the square, it is a vertical shift. Now, once we know that it's horizontal and vertical, we want to know which direction. Horizontal could be left or right, vertical could be up or down. So the minus or plus is going to indicate whether you are going left or right and up or down. So with a horizontal shift, if you have a minus, that means you're going right. And with the vertical shift, if you have a minus, that means you're going down. So we're going to go right 7 and down 9. So what I'm going to pay attention to is that 0, 0, where the vertex was that we talked about earlier. If we take that point of 0, 0 and shift that point to the right 7 and down 9, that's going to get us to the new location of our vertex. So we start at the vertex, go to the right 7, go down 9, and that is the new location of our vertex. We started out having an up-facing parabola. We'll continue to have an up-facing parabola. You would only turn it into a down-facing parabola if you had a reflection, which would be a negative. So we have an up-facing parabola, and that is the sketch of our quadratic function. The diagonal of a TV set is 39 inches long. Its length is 21 inches more than the height. Find the dimensions of the TV set. Make sure to show all your work to receive full credit. So on this example, we're talking about a television set that's going to be in the shape of a rectangle. And we're told that the diagonal of the TV set is 39 inches long. And the diagonal goes from corner to corner. I'm going to label this side as the width and this side as the length. I typically put whatever side is longer as the length. And then we have a statement here that says the length is 21 inches more than the height. So maybe I should call this the height instead of the width. The length is 21 inches more, 21 inches more than the height. And we want to find the dimensions of the TV set. So I can label this length with height plus 21. And then as I look at this, I can notice that if I look at the length and the height and the diagonal, that creates a right triangle. And a right triangle can be used with Pythagorean theorem. So Pythagorean theorem is when you have a right triangle and you have two sides, we call those the legs, and then the side that's opposite the right angle, we call that the hypotenuse. And Pythagoras says that there's a relation between these sides, and the relation is that a squared plus b squared equals c squared. So we can use that relation that we have in our picture. 39 will be the hypotenuse because it's opposite of the right angle. So we have h plus 21 squared plus h squared equals 39 squared. So if we're able to solve this equation, we'll know the value of the height and then ultimately know the value of the width, the length. So let's work this out. We need to do h plus 21 times h plus 21 plus h squared equals 39 squared. I think I might need my calculator to help me with these big numbers. So 39 squared is 1,521. I'll multiply this out. H times h is h squared. H times 21 is 21h. We have another 21h. And then we need 21 times 21, which is 441. I carry down that plus h squared, and this equals 1,521. I'll combine like terms. H squared plus h squared will be 2h squared. 21h plus 21h will be 42h. And we have 441 equals 1,521. So I can see now that I have a quadratic equation. I'll subtract this 1,521 on both sides so I can move all the terms to the same side. So 1,521 minus 441 would be 1,080, and that should be negative. We have 2h squared plus 42h minus 1,080 equals 0. I want to try to solve this quadratic. I'm going to start by solving it with factoring, but if I'm not able to factor, I will try to use the quadratic formula. Quadratic formula always works. So first I notice that all of these numbers are even, so I can factor out a 2. That would give h squared plus 21h minus 540. And then I'm going to look for factors of 540 that could create a 21 in the middle. So let's look at 540. That's 1 and 540. 2 and 2 goes into there. 270. 3 goes into there. I'm going to use my calculator to help. 540 divided by 3 would be 180. 4 will go in there. 540 divided by 4 will give me 135. Okay, it ends in a 0, so 5 will go in there. 540 divided by 5 be 108. None of these get me anywhere close to 21 so far, so I've got to keep going. Let's try 6. 540 divided by 6 would be 90. I don't think 7 would go in there, but let me try it anyway. Okay, 7 does not go in there. I don't think 8 will. How about 9? Yes, 9 will. 9 times 60. 10 times 54. And then I don't think 11 does. About 12. 540 divided by 12 is 45. And let me subtract those two. 45 minus 12 does not give me 21. So let me keep going. I don't think 13 works, but let me double check. Okay, 13 does not work. 14 won't work. 15 might. Let's try 15. So 540 divided by 15 is 36. 15 times 36. And 36 minus 15 does give me 21. So there's the pair I was looking for. So let's factor this into h and h. 15 and 36. I want the positive on the 36 and the minus on the 15. I can then set each one of these factors equal to 0. And that gives h equals 15 and h equals negative 36. Remember, h stands for the height, so having a negative height doesn't make sense. So this is our solution of having a height of 15, and then the length will be 15 plus 21. That's going to be 36. So the dimensions of our television set will have a height of 15 and a length of 36. So that is the dimensions of our television set. Length, 36 inches, height of 15 inches. Mark, the red graph, and Iris, the blue graph, are driving two separate cars to San Francisco. They begin the trip with full gas tanks. The amount of gas in gallons that remains in each car depends on the number of miles driven, as shown to the right. After how many miles will the tanks contain the same amount of gas? If the number of miles driven is more than this, which car will have more gas in its tank? So let's take a look at the graph and make sure we understand it first. So we see on the right-hand side that the scale is labeled miles driven, and we've got 0 to 600. So this scale goes from 0 miles to 600 miles driven. And then on the vertical axis, it's labeled as gallons of gas in the tank, and it starts at 0 and goes all the way up to 60. So as mentioned in the instructions, Mark is the red graph and Iris is the blue graph. So here we have this line. The red line is Mark's trip, the record of Mark's trip. And in blue, we have a record of Iris's trip. So it says here, after how many miles will the tanks contain the same amount of gas? So the same amount of gas, remember this vertical scale is the gallons of gas, and we can see at this point right here, that's when the gallons of gas are the same. And if we go down here, we can see that at 250 miles, the amount of gas will be the same. So we know that after 250 miles driven, the amount of gas in the tanks is the same. Okay, so let's take a look at the second question. If the number of miles driven is more than this, which car will have more gas in its tank? So we're talking about the number of miles now. So this is on our X scale. Is more than this, so we're talking about to the right of that point, to the right of 250 miles, which car will have more gas in it? So on that portion of the trip, you can see that the red line is higher than the blue line. So during that portion of the trip where you have driven more than 250 miles, you can see that the red graph, which is Mark, has more gas in the tank because it has a higher Y value. Remember, the Y part is the gallons in the tank. So Mark's car has more gallons of gas after 250 miles driven. Thank you for checking out my videos. Have a great day.